Page 15 of Chapter 16, Euler's Complex Numbers of MHL, number 8b. So we're continuing from the previous page, 8a, in which we found out that the number z, the complex number z, had a modulus of 1 and an argument of negative 2/3 pi. So we could write that z is equal to 1 cis negative 2/3 pi, right? And B says, show that z is a cube root of 1. So if z is a cube root of 1, then we should be able to cube it and get 1, right? So, and if we're going to cube root this, then we could write that as we could write that as 1 cubed cis 3 times negative 2/3 pi, which is equal to 1 times cis negative 2 pi. And negative 2 pi is the same thing as cis 0, so that's equal to 1. So, okay, we've shown that z is a cube root of 1. Without using a calculator, show that this is a real number. Okay, so the first term, or the first factor, 1 minus 2z, let's see if we can figure out what that is relative to this. So let's rewrite z as a plus bi first, shall we? I don't know if we should do that first, or I don't know if we should figure out what this is. Let's multiply it out first, okay? So we'll get 2z squared minus 1 minus 4z cubed plus 2z. Now let's put it in order. 4z cubed plus 2z squared plus 2z minus 1. Let's see, we already know that z is a cube root of 1, so here this turns into 1, so it's just minus 4, right? And then plus 2z squared. 2z squared, z squared would be 1 squared times 1 squared times cis negative 4/3 pi. Negative 4/3 pi would be 30, 60, 90 triangle looks like that. So that would be, we could rewrite that as 2/3 pi, right? So that would be cis 2/3 pi. So we could put that here, cis 2/3 pi. And then plus 2z, which would be plus 2 cis negative 2/3 pi. And then minus 1. Now we can kind of see where it could be a real number. So this and this is real, right? And if we have 2 cis 2/3 pi and we have 2 cis negative 2/3 pi, aren't those two complex conjugates? And when you add two complex conjugates together, you get, you cancel out the imaginary parts, right? So if we have 2/3 pi, and when the hypotenuse is 2, then we know that the real component for this one is going to be negative 1, the real part, and the real part of this one is going to be negative 1 also. and the imaginary parts are going to be opposite and they'll cancel each other out. So we'll have minus 4, minus 1, minus 1, minus 1. So the whole thing is going to be minus 7. And it's a real number, right? So according to the page 503 reading, the nth roots of unity are the solutions of z to the n equals 1. So the unity they're talking about here is the 1 here. If omega is the root with the smallest possible argument that is not 0, then the remaining roots are exponents of omega. So a good example of that is, let's say that you were finding the cube roots of 1. If we draw the complex number 1 in the complex plane, it is a vector going in the right direction, like that. And if we were to find all the cube roots of it, we would have 3 complex numbers. One would be pointing exactly in the same direction. One would be pointing 120 degrees like that, and the other one would be 120 degrees separated from those. Those are the complex cube roots of 1. And what they're saying is that they can define all the cube roots of 1 by defining first the smallest argument root, which is this one here, as omega, and then that would mean that the other roots are powers of omega. So like this one would be omega squared, for example, and this one would be omega to the 0 or omega cubed. Okay, so for a cube root, you could define the 3 roots as 1, omega, and omega squared. Okay, so let's take a look at the problem they gave us. So they said they give us z plus 3 quantity cubed equals 1. So let's give the answer in terms of omega. So z plus 3 cubed equals 1. And we know that the cube roots, the complex roots of 1, are given by 1, omega, and omega squared. So what we could do is we could say, okay, z plus 3, which is the cube root of 1, is equal to omega to the n, where n is equal to 0, 1, and 2. So we could actually say that z is equal to omega to the n minus 3, where n equals 0, 1, and 2. Now if you want to see exactly what the z values would be, the first z value would be n equals 0, so omega to the 0 is 1, minus 3 is negative 2, right? If you plug negative 2 in here, you can see that it actually works. Negative 2 plus 3 is 1, 1 cubed is 1. What would be the second value? The second value would be omega to the first, so it would be omega minus 3. And the last one would be omega squared minus 3. And what exactly is omega? Omega, in this case, is going to be the root with the smallest argument that's not 0. So it would be cis 2 pi over 3, like we drew in the Argand diagram. Okay? All right, let's look at this one. Okay, for this one, remember that we need to express it as z to the n equals 1. And this one basically has a complex number cubed equals 8. So the first thing we need to do is make sure that the right side is 1. So we're going to divide both sides by 8. So we're going to get z minus 1 cubed divided by 8 equals 1. Okay, then we're going to group the z minus 1 with the 8. So we get z minus 1 divided by 2 cubed. Z minus 1 divided by 2 cubed equals 1. Then we know that the cube root of 1 is equal to the omega, where omega is cis 2 pi over 3. And then we know that the 3 cube roots are going to be omega to the n, where n is equal to 0, 1, and 2. So we're going to say that z minus 1 divided by 2 is equal to omega to the n, where n equals 0, 1, and 2. So let's solve for z. So z would be equal to 2 omega n plus 1. And let's look at what the three solutions would be. One of the solutions would be 2 times omega to the 0 plus 1, which would just be 2 plus 1, which is 3. And we can see that if we did put 3 in here, we would get 3 minus 1, which is 2. 2 cubed equals 8, so that works, right? And then we'll put n equals 1, so that would be 2 to the omega to the first, which would be 2 omega plus 1, and omega, remember, is cis 2 pi over 3 plus 1. And then the other one would be 2 cis 4 pi over 3 plus 1. And so those would be the three solutions. Okay, let's look at the third one. So this one has 2z minus 1 cubed equals negative 1. Remember again that on the right side we need to have 1. So we're going to divide both sides by negative 1. And we'll get 2z minus 1 cubed divided by negative 1. And then we're going to try to group it inside the cube. So we'll get 2z minus 1 divided by negative 1 cubed. That works too, right? Because if we cube the negative 1 in the denominator, it becomes the negative 1 we have here, equals 1. So now we know that our omega is actually equal to 2z minus 1 divided by negative 1, or we could just say it's negative 2z plus 1. We're going to set that equal to omega to the n, where n is equal to 0, 1, or 2. Then we're going to solve for z. So we're going to have omega to the n minus 1 divided by negative 2, and that will be equal to z. So this, for n equals 0, would be 1 minus 1 divided by negative 2, which is 0. And then for omega to the first, it would be omega minus 1 divided by negative 2, where omega is equal to cis 2 pi over 3. And the third one would be omega squared minus 1 divided by negative 2. So those would be the three solutions for z. Okay? Now we're going to do part B, where it says show by vector addition that 1 plus omega squared equals 0. So if we know that omega is cis 2 pi over 3, then let's show that this is true using vector addition. Well, let's draw cis 2 pi over 3. So 2 pi over 3, remember, is about 120 degrees. And so omega would look kind of like that, and a vector pointing in the direction of 120 degrees from 0 degrees. And the vector 1 would be a vector that's pointing directly to the right, and omega squared would basically be cis of 2 times 2 pi over 3, or 4 to pi over 3, which would be 240 degrees. So do you see how, like, 1, omega, and omega squared are all pointing 120 degrees different than each other? So if you put these vectors head to tail, you would have the 1 vector there, and then you would have the omega vector there, and you would have the omega squared vector there, and then if you add them all together, they sum up to 0, right? That's all you need to do. Here it says for 3a to find the 5 fifth roots of unity and display them on an argand diagram. So if we drew an argand diagram with a unit circle on it, the first root would point directly in the direction to the right as positive 1. And then the other 4 roots would be equally spaced around the unit circle, kind of like this. And the question is, what is the angle between these roots? It would basically be 360 divided by 5, or 2 pi divided by 5. So each one of these angles here, which would be 2 pi divided by 5. Okay, so the fifth roots of unity, the omega in this case would be cis 2 pi divided by 5. If omega is the root with the smallest possible argument, show that the roots are 1, omega, omega squared, omega cubed, and omega to the fourth. Okay, so basically if the first angle, or the first argument is 2 pi over 5, we know that the second angle would be 4 pi over 5, and we know that the third angle would be 6 pi over 5, and we know that this angle would be 8 pi over 5. And the last angle, or the first angle actually in the last angle, is going to be 10 pi over 5, which is equal to 2 pi, which is exactly what we should get, right? So it worked out. So we know that the 5 angles should be 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5. And if this one is omega, because it's the smallest argument that's not 0, then obviously the other ones are going to be omega squared, omega cubed, and omega to the fourth, right? Because omega is 2 pi over 5, omega squared in terms of cis is going to be 2 times 2 pi over 5, which is 4 pi over 5. And the next one is going to be 3 times 2 pi over 5, which is equal to 6 pi over 5. And the last one is going to be 4 times 2 pi over 5, which is equal to 8 pi over 5, right? So, we have shown that that is true, right? All right, because this one is omega to the fourth. This one is omega cubed. This one is omega squared. And this one is omega. All right, I think that's done. And the first one, of course, is 1. That's it for this page.